Okay, so let's get started. So human languages order information efficiently, and efficiently, I mean efficiently for the listener. So efficiently in terms of the processing cost for the listener. So the hypothesis here is that language is set up to make it easy to process by the listener, and we measure that by two factors: dependency length and n-gram word probability. And these are both factors that have been shown to correlate with processing times in people. And so the talk will be sort of, the first half will be about dependency length, and the second half will be about word probability and about the interaction between the two features. And the dependency length part is the part that Davey is the co-author. So this is based on a paper that we had in Journal Cognitive Science in 2010. And the second part is some project Florian and I have been working on, and we are getting ready to publish it. I have a draft that I can send you if you ask me after the talk. So dependency length. So these are, this is a picture of dependencies for an example sentence. And the idea of dependency grammar is that every word has a head, every word modifies some head, and dependency is a relation that goes from a word to its head. And so, for example, a subject modifies its verb. A man arrived, and a determiner modifies its noun. An adjective would also modify its noun. Relative clause modifies the main verb, or can modify a noun. And so there's some kind of tree of these dependency relations, because every word has one head. And we're also assuming that the dependencies don't cross. So when you draw them, when you put the words in order and draw them out like this, you're not allowed to have, say, a dependency going from here to here crossing this line. And so we're going to be working with these trees. We're working with data from the Penn Tree Bank. Penn Tree Bank data looks like this. So it has trees that have nodes for different phrase types like noun phrase, and verb phrase, and sentence or clause. And we have a pretty standard deterministic process that extracts the dependencies from these trees. So there's a set of rules that look for it. The head word of each phrase. So, for example, arrived is the head word. The main verb of the sentence, the head word of the main clause. And so, applying the dependency from the head word of this phrase to the head word of this phrase that it's sibling with, and that's where the dependencies come from. So it seems like a reasonable principle in general that dependencies should be short. Things should be arranged to make the dependencies short. So the idea is you don't, the longer the dependency is, the longer you have to keep that word in memory before you can integrate it with whatever it's connected to in the syntax and the sense. And people in linguistic typology have talked about this as possibly a motivation for the idea that languages are either always left-headed or always right-headed. So, for example, this language, all of the arrows point to the right, so this would be a right-headed language. And you can sort of see that there's tends to make the dependency short. So if you have a long chain like this, and all the arrows point to the right, then each arrow is only one word long, and that's going to tend to make the dependency shorter. Well, it's not true that languages are really always right-handed or always left-handed. The example we had on the slide earlier did not have all the arrows pointing in the same direction. But that could also be a reason for, or that could also potentially be motivated by dependency lines. So, for example, here you have a chain of 3 words, and 3 words pointing to the left, 1 word pointing to the right. And this is obviously the minimum dependency length. Out of all possible word orders for the sentence, this makes the arrows as short as possible because they're all only 1 word long. And that happens because this word has its two dependents on either side. If we put this on this side, it would have to have a longer arrow. So dependency length could also be a motivation for alternating headedness. And we're going to talk about in this talk, the dependency length part is, first of all, if you have a tree, how do you make the dependencies as short as possible? So there's a simple way of doing that in linear time. And, but that assumes that you can put the word order for any particular sentence in any order that you want. And English word order is fixed, so the subject always comes before the verb. The object always comes after the verb. So we want to work with grammars that have fixed word order in terms of label dependencies. So the labels on the dependencies are relations like subject and object. And we want to find a grammar where we put the label dependencies in some fixed order. We get to choose the order, and we want to optimize the dependency length to make it as small as possible. Then we want to see whether English actually looks like the grammar that we get by doing that optimization.
Is the optimal length always unique?
Well, a whole lot. So here's how you find the optimal length. So so first of all, to break the problem down into pieces, you want to break some subtree from the rest of the sentence outside of this link that connects it to the rest of the sentence. And the way to do that is the length of this link has a contribution that depends both on how stuff is ordered within here. That affects how long this piece of the edge is, and how stuff is ordered in the rest of the sentence. That affects how long the right half of the link is. So what we do is we break the link into two pieces. So then you can just look at this subtree independently and include this piece of this link in the contribution from that subtree.
And so the question is, you're saying English relative to what? English is optimal, or is effective in terms of dependency lengths relative to what other languages?
Relative to other possible orders in which you could put the words of English. Okay, so it's not really looking at other
Languages, but
yeah.
specifically English.
Yeah. Okay, so if you want to make the dependency lengths as small as possible, it also makes sense to put the shortest subtrees closest to the head that they modify. So there's some group of words here, and this is, if you order them by length, this is shortest, next shortest, next shortest. Then all the arrows on this side have to cross however long this is, and if this is what's closer to the root has more arrows going over it. So if you have something that's shorter outside of something that's longer, you can improve the total length by switching those. So you can always make the dependency length shorter by pushing the smaller subtrees closer to the root. So, so if we had all the children on one side, we would know exactly what to do. But what about figuring out who goes on the left and who goes on the right? Well, you have to have you want to have the two longest subtrees on opposite sides. So, for example, here, the two longest subtrees are the ith longest, and the I minus 1's longest. Then we can improve this tree by moving this over to the other side and putting the outermost on the other side, and swapping whatever was outermost on that side. So from these two things, putting them together, that means that the optimal dependency length is achieved by ordering shortest to longest and alternating left and right. So 1, 2, 3, 4, and so on. And so there's not necessarily one layout there may be other layouts that achieve that number, but that will always give you the optimal number. Okay, and you can prove that by induction on the number of children based on the two properties I just showed you. So we do this for the real English trees from the tree bank. We extract the dependencies based on the head rules that I talked about, and then you take those trees and reorder them according to the algorithm I just gave you, shortest to longest inside out. And so the basic assumption is that somehow the trees represent the meanings of the sentences, and those are fixed. That's the information that the people have to convey. And the English grammar gets to decide what the word order should be, and we'll compare different word orders in terms of dependency length. So here's what happens. So this is the average total dependency length for a sentence, and this is the best you could get with the algorithm I showed you. This is the real average in the real data, and this is what you would get by just randomly choosing some order for the trees where the dependencies are not allowed to cross, but the layout is random. And English is much lower than random, so right away that's an indication that English is somehow designed to keep dependency length small. It's not as close, or it's not as low as you can possibly make it, but it's actually most of the way there. And as I said, this optimal algorithm means that the word order is different for every sentence, so it doesn't have the property that the subject is always to the left, for example. So really we want to look at fixed word orders. And so we're going to label each dependency with pairs of non-terminal labels from the tree it was extracted from. And that tells you what the grammatical relation is. It will encode whether something is a subject, an object, an adjective modifying a noun, or so on. And then, so each of those dependency types will give them some weight, and we'll order according to those weights. So a negative weight means it's to the left, and a positive weight means it's to the right, and a larger positive weight means it's further to the right. Okay, so for example, we have these 3 dependency types. These mean a determiner inside a noun phrase, an adjective inside a noun phrase, a prepositional phrase inside the noun phrase. This would basically do what English does. It says these 2 are on the left, the determiner is further left than the adjective, and the prepositional phrase is on the right. And the reason we did it this way is that it doesn't matter how many dependents a word has. So this is like saying noun phrase has a determiner, some adjectives, and a head noun, and then some prepositional phrases, and adjectives themselves. If it has more than one adjective, those can come in any order. So this doesn't decide that. And if there's no prepositional phrase, the adjective is still to the left. So it's not a rule that looks at all of the children at once. Okay, so we want to find the grammar with the shortest dependency length. So that means the total dependency length. Lambdas are the numbers I showed you on the last slide, and we want to pick the numbers to make the dependency length as small as possible. You think of this as a function of lambda. What does it look like? Well, it's not convex, and it's piecewise constant. So it's piecewise constant because the dependency length is an integer, and it doesn't change until one of the weights crosses over the value of some other weight. So the positions of 2 things switch. So you want to choose the weights. The problem I showed you, it's NP complete. The way we do it is with coordinate descent. That means you adjust one weight at a time. And you can figure out all values of the function as you adjust one weight, because the function only changes when you cross some other weight. So you can make a list of what are the other weights that this weight can cross, what are the other dependency types that this would reorder with, and just consider all values of that weight in those intervals between things that it interacts with. And so to compute the new dependency length, you have to look at the whole corpus and compute new dependency lengths for every sentence in the corpus. You can make that more efficient by indexing, first of all, for each weight, which are the other weights that it interacts with. And if you change that weight, which sentences will have their order change. So you can just compute the dependency length for a small fraction of the original sentences. Okay, so here's what we get when we do that. So this this is the same number I had before. This is the total dependency length. So this is a completely random order. And this is measuring how often a word has all of its children ordered in the same order that they appeared in the real, the original sentence. Okay, so we came up with a method for extracting weights from the optimal layouts that I showed you. This is if you use the weights from the positions that things actually occurred in English. And this is the result of this optimization procedure that I had on the last slide. And so the first thing to notice here is, okay, how often do things have things in the same order they were in the original sentence? So even if you look at the English and computing your weights, this number is not 100% because there is some freedom in how things are ordered in English. And there are also cases where, say, you have two adjectives and you have no basis for picking the two orders. So if we look at the optimized weights, their dependency length is it's smaller than English. So that means if you really are trying to push down dependency length, you can push it smaller than English. But it's kind of close, and it's much closer than, let's say, the real is to the random order. And it's also better in terms of actually matching the real order 64% of the time, which is more than you would get by chance. Okay, this is just to show text versus speech, spoken language. Most of our data is from the Wall Street Journal, and we also did this for the switchboard data set, which is conversations, and basically it's the same. So the big difference is that the switchboard sentences are shorter, so the average dependency length is 42, it's 12, but the basic effect of the optimization is really the same. And these are some examples of weights that we get out. So, for example, the subject really is before the verb, it has a negative weight, and the object is after the verb, it has a positive weight. And let's see, determiner is before the noun. So we distinguish between subject and object now. So it would be possible for these to be different, but they're actually both the same. So the determiner comes before the noun. And so those agree. Actually, with English, they don't all agree with English, but I don't know, give you some idea. Okay, and this is to show you how many sentences, does it matter how many sentences you use to run this optimization procedure? And if you have more data, you can get sort of closer to the matching the real English, but actually even with a very small number of sentences, you can do pretty well. So it doesn't, even with say 500 sentences, you're in the same ballpark. And basically that's just because there's not a huge number of parameters in the model, I think. So it's all pairs of non-terminals in the grammar. Okay, so that's basically the first part of the talk. And the conclusion is that English word order seems to minimize dependency length. So one thing I haven't talked about is the fact that, well, English word order is not totally fixed. So you can say he quickly ran. Long modifying phrases, long preposition phrases can be extracted. There's topicalization versus given information. So obviously none of that is taken into account. We just talked about English. There was a paper earlier this year that did exactly the same experiment I just showed you for 37 languages, and they all have dependency lengths shorter than random. I'm not sure it's random. They didn't do the optimization part, but they compared random to the real dependency length in the language. And this was in PNAS. There was some stories about it in the press, and it was kind of funny. One of my relatives forwarded me this story that he saw in the Huffington Post. He said, "Oh, you might think this is interesting." I tell him that that was our idea. Yeah.
Just to clarify, in the previous slide when you're talking about the correct, I don't remember for sure. I think is that the percentage of words whose dependents are completely ordered correctly?
Yes, a percentage of words, all of whose dependents are ordered correctly. Yeah. Any other questions?
Sorry, is this the word that like? Is there any historical evidence that languages have evolved towards being like shorter dependency length?
So no, I mean I don't know about Old English or whatever, but I sort of think this means this must have happened. So
There's the research by
Yeah.
Untitled, right? 2010
Okay.
PhD thesis that shows that English, when it was case in kind of 1100 AD, from then on to now, it has systematically shortened dependency. Both in noun phrases and the verb body.
So okay, so let's talk about the probability part. So when I say probability, I really mean n-gram probability. So when we had this sentence, when the man arrived, we're going to model the probability of each word by looking at the two previous words. So starting with when conditioned on the beginning of the sentence, the after the beginning of the sentence, and when, and so on. And we call it information or surprisal. Information is the same as negative log probability, so higher probability means lower information. We sort of already knew that was going to happen. It's been shown that things with high probability are easy for people to process. They take less time for people to process. So information correlates with processing time. Higher information is lower probability, higher processing time. So to measure this exactly, this is our measure of the information in the language. So we're going to be trading off these two factors, dependency length and information, and this is the equation for information. So it's, like I said, negative log probability, log of 1 over probability, and this means the lambdas are the weights for the dependency relation. So for language specified by a certain set of dependency weights, its total information is the average n-gram probability. And these probabilities are computed by ordering all of our data according to this grammar, counting n-grams on some test set, and then evaluating these probabilities on some outside. And so this would be for one word, an average over all words in the data. And then there's also the question of how long the words are. So this is normalized to adjust for the length of the word. And the idea would be that if the word is longer, people have more time to process that word, so it would make sense for information to be spread out over time. And that depends on the length of the word. So we actually measure the length of the word in letters, not phonemes. And actually, we don't measure it in letters, so we're going to do several languages. We measure it in characters. So for Chinese, it's Chinese characters. And that's why we have this term here. K is the number of characters in your writing system. So this is just kind of to try to make these numbers comparable across different, whether you have an alphabet or Chinese characters. Okay, so here's the setup for the whole experiment. You have your data, you extract all the dependency types, and we're going to make random ordering. So that means we choose the weights for each of these relations randomly. We do it 1,000 times. We make 1,000 different random grammars. And we reorder the data according to that, each of those grammars. And then we compute the information density and dependency length on the reordered corpus. Okay, so this is the data that we used. We had 5 different languages spoken in English. And maybe we could do it for 37 languages, but I'm afraid to, because I think you need more data now. So to compute n-gram probabilities, there's a lot of n-grams, so you need more data to estimate them. So we're doing languages where we have these 6,000 sentences that have been annotated with trees. And here's the average sentence length. And so this is the one spoken data set that has much shorter sentences. Mostly it's newswire. Okay, so each point on these graphs is one of the random grammars, one of the random sets of weights, and the x-axis is average dependency length per word, y-axis is average log probability per word, negative log probability per word. And just looking at this, you can sort of see there's some correlation. If you go to the right, you sort of tend to go up, but maybe not too much. It's not all on a straight line. So why would they be correlated? Well, if the dependencies are short, then that means that words that are related tend to be next to each other if all the dependencies are one. So it's probably easier to predict the word. So it would be inside the n-gram window, and it's probably easy to predict that word given its word. But that's not a strict relationship, as you can see. Okay, and this is just per word rather than per character. It doesn't really make much difference whether you do per word or per character. And I said they were correlated, so this is the coefficients of correlation. As you can see, they're correlated, but not that tightly. Okay, so this is what happens if you put the real grammar on there. So you measure the dependency length and the information density for the real grammars. Basically, they're all down and to the left. So they have lower information with higher probability. You have shorter dependencies. And it's true whether you have Czech, which people say is a free word order language. So really, it's also true if you have Chinese, which, for example, doesn't have any inflection. So, we're not taking any of these things into account. Our n-gram probabilities are just, they're inflected words. There's a lot more words for Czech because it's very highly inflected. You see basically the same pattern for all of these languages. And again, this is the same thing for measuring information at word level instead of character level. And this is the numbers for the same experiment, and it's how often is the real grammar lower or better than the random grammar. So out of the 1,000 random grammars that we had, how often did the random grammar have lower information, higher probability than the real Czech word order? And basically never. Okay, so these are p-values. These are how often would we expect this to happen by chance, randomly generated 1,000 grammars. How often would they match the real grammar in terms of these different measures? And so most of the numbers are 0. The sections are English and Czech for the information density, and German for the dependency length. Oh, it's German and Chinese for the dependency length.
I mean, Mandarin is very curious case direct dispatch rather than, I think, didn't include it and it's the dependency length.
Right. Yeah. And it's only the most widely spoken language. Okay, so now we're going to do the optimization that we did before. So we're going to pick the weights. So before we were picking the weights and we were just looking at the dependency length, and now we're adding this term. This should be alpha times h of lambda. So, so this is the information density h of lambda, and we can vary the trade-off between those two factors. So alpha is the weight of that trade-off. And so the procedure is the same, optimization procedure is the same. It's more expensive computationally because if you remember the part where I said you can only look at the sentences that happen to reorder, you can't do that anymore because now all of the n-gram probabilities have changed. So you have to recompute the n-gram probabilities for every sentence. Okay, so here we have the random languages, the real language, and the optimized languages that we get by varying alpha. So this is sort of the efficient frontier if you trade off between dependency lengths and information density. How important is it to trade off one or the other? And basically what this shows is that you really you can push further than the real language. You can always get further to the left than the real language. But the real language is kind of close compared to the random languages. Okay, and this is figures for the same experiment. So optimizing for just information density, just dependency length, or this is trading off with lambda 1, so equal trade-off between the two. And you can see that there is a cost. So if you just want to make the dependency length as small as possible, you can do that, but your information density would be higher than if you were just trying to make information density as low as possible. And the real languages seem to be somewhere in this trade-off. So I think it's interesting that there is so much of a difference according to how much weight you give to dependency length versus information density. So I said that they should correlate because short dependencies make it easier to predict the next word, but there's obviously limits to how strong that correlation is. And so somehow they are different factors, and the real languages seem to somehow make this trade-off and push information density low and dependency length low. Okay, and then this is just putting all the languages on the same graph and measuring the distance from the optimized language, the real language to the optimized language. And this is, so real language, the optimized language, and this is optimized with equal trade-off between information density, dependency length, and sort of they all up to the left. Okay, so that's it. There seems to be some trade-off between dependency length and information density. And the real languages pretty consistently across the language seem to optimize both factors and make this trade-off between the two. Questions? Yeah.
Wondering if this accounts for either of the factors you consider, accounts for the fact that heavier constituents can be further from their head than light constituents.
It doesn't. It really doesn't, because it just looks at the relationship, the syntactic relationship. So when we reorder our sentences according to our grammars, it doesn't get to look at that factor.
But it explains it. Right, so heavier constituents, more words, and then usually more syntactic nodes.
Well, that's what I'm asking, whether it explains it.
Yeah, so that's.
Oh, okay, okay. So it explains, it doesn't explain the fact that something, that a very long relative clause can be extraposed.
Or even an adverb.
But it does.
Can be further to the right.
Right, so it does, so we don't allow things to vary like that. But it does, because it wants to put things that are on average shorter closer to the end. It will tend to put shorter things closer to the head and longer things.
So in that sense, it does explain it.
Have you done any analysis on your data to see if there's any trends in the differences in the real data versus your optimized data?
It's hard to figure out how to do that. So so I showed you one optimized grammar, and you can sort of look at it, and you can sort of see maybe why it did certain things that where it does or does not agree with English. But the thing is that if I run my optimization procedure 10 times, I get 10 different grammars out. So I'm not guaranteed to find the global optimum. Okay, and what you see is that the grammars that you get out they're very similar in terms of these numbers, in terms of the dependency length and information, but they're not the same grammars. So it's hard for me to even say really what is the if we were optimizing, should this particular relation be to the left or to the right?
Okay, but for the real data, you can identify places that have coefficients that are going beyond the optimal, and you can take a look at those sentences and see maybe why.
Oh, okay.
I guess that's what I'm really
okay.
more interested in what the real data is doing that takes it beyond whatever optimum that you've established.
Yeah, but I don't know. Yeah.
I think the second part of the engram stuff that is getting an interesting issue that I've thought about, which is to what extent are the conventions for dependencies really the ones that maximize, I guess, mutual information. So, for example, with prepositional phrases, if you have a prepositional phrase modifying a verb, does the verb tell you more about the preposition or about the prepositional object? I don't think that's obvious. And, I mean, what this is telling you, I think, is that dependency relations they must be pretty good, but they're not.
Yeah. So
they're not
maybe
necessarily optimal.
or maybe if the preposition tells you more about its object, then when you optimize the grammar, it will try to make that particularly short, and maybe at the cost of making the relation from the preposition to its head longer.
If the verb, sorry.
Okay, so the preposition, let's say, tells you more about its object than about the verb that it modifies.
Well, I was saying, does the verb tell you more about the preposition or about the object? That is,
okay.
There's this convention that we attach the verb to the preposition. Well, why not attach the verb to the object of the preposition? Why not make the noun
I see.
to the head of the preposition? Right.
I see. So yeah, okay. So we assume that the dependencies come from God.
Sure.
Yeah.
Yeah, but I mean, they're not completely.
Yeah.
There's a complete consensus.
That's right.
A lot of linguists think that the determiner is the head of the.
Yeah, and nobody knows what to do with conjunctions, so that's another.
Maybe I can jump in there. So, I mean, one other way to look at this is if it's costly for you to maintain things in memory and you want to have predictive information locally, right? So you could imagine an experiment even more computationally expensive. So where you free yourself from the dependencies, you calculate pairwise mutual information between parts of speech and sentences, and then ask how local are they kept. Does that temporary information predict how local you keep it, right? So that's So in the framing of the paper, we actually kind of walk a little in that direction, saying it's about locality of predictive information.
I wonder, this probably would require doing this sort of joint optimization of information density and living on like way more than just 5 or 6 languages. But I wonder if you can, you have this nice kind of optimal frontier, and you can ask like, and you can parameterize that frontier by this trade-off between information density and dependency length, right? And so you can project the actual language somewhere on that frontier and say, like, well, how much does this language appear to be trading off information density versus dependency length? And then I would be curious to see if that relates to any other kind of typological properties of these languages, right? That aren't explicitly about dependencies, or maybe a particular kind of dependency that predicts whether they're going to be putting more or less weight on dependency overall.
Yeah, that's interesting.
Like, do you have any intuitions or hunches about that?
Good in our sense.
Yeah, right.
It's
It's small, yeah.
Is there any, I guess, indication in what you've looked at so far about whether the real languages, their current set of weights for these dependencies, are in local minima, so that if you define some threshold that would be a reasonable weight adjustment, I have no idea what a reasonable weight adjustment would be, but that if you searched in every direction for single weight adjustments, that the solution would actually be worse than the natural language. And that this might say something about sort of the solution that languages have reached and when or whether they can continue to approximate the optimum.
Yeah, so that's, I suspected that is actually not the case because our procedure finds local minimum. That, you know, so it can get trapped as well. And so the fact that it's further down and to the left tells me that probably the real languages are not trapped in local minimum.
So your information density measures
The mean over words of,
yeah. So if you made it the variance, if that was the thing you were optimizing,
that's what we did first, and it didn't work. Okay, so
if that doesn't work, it seems like a really interesting failure.
yeah. So the reason is that the mean, if you optimize the variance, you end up with higher average information. I mean, it's sort of like you have to push some things up to get the variance as small as possible. And yeah, so it seems like that's not what's happening. So
it seems like any other summary statistic or something you could compute would be interesting, right? Like our language is structured to avoid giving me too many bits in a short amount of time. You know, independent of the variance, maybe I just don't want to exceed the channel capacity, or I don't want to undershoot the channel capacity. Like anything you could compute.
right, yeah. So I thought that, so I thought variance made sense because because it penalizes you for overshooting, at specific points, and maybe.
But it depends on what the cost function is. Like my cost function might just be if I exceed the channel capacity, that costs something. Until I do, it doesn't matter.
And even variance is it's based on squared error, so you can have like absolute value or all kinds of things.
So it was really nowhere close, right? So I think the problem is that when you penalize for deviation from uniform, then the optimized languages basically make everything less predictable. So that is the easiest fix. You have a few things that are really predictable and determined, so you put them in really shitty places, and that optimizes that value quite easily, but it makes intuitively no sense that their languages are there. So you would have to jointly optimize variance and information density and dependency length.
Even when you're looking at character per character, because the really predictable words are short.
You could constrain mean density and optimize variance.
Yes.
I mean, if you could do that. I don't know if you could.
Okay, thank you very much.